Hello, let's discuss basic concepts of number theory. When a number is called prime, if it have no other divisors other than 1 and the number itself. For example, 11, 9 and 23. Given a number n, how to find whether it is prime or not? We can traverse all numbers from 2 till n, and if we find any divisor, so the mod will be 0, and then we can return 0 because we found a divisor and surely it is not a prime. So finally we can return 1 if we did not find any other factor. So the time complexity of this will be of n. So if I try to find factors of 36, they are 1, 2, 3, 4, 6, 9, 12, 18 and 36. So if we observe one thing, for every number which is less than square root, have another divisor 36 by that number which are greater than 6. So there is no need to traverse all the numbers. We can just traverse root n, and if we did not find any other factor in this, surely there will be no other factor in this as well, because for every number here there exists here as well. So we can traverse from 2 till root n, and if we find any divisor, we can return 0, it is not a prime, else we can return 1. So the time complexity of this is root n because we are traversing only till root n. So this is a significant drop. For a given number, O of root n is an optimal one. But what if we are given q queries and we have to find whether the given number is prime or not? So if q is up to 1 is 6 and n is up to 1 is 6, for q queries if we use the second one, the time complexity will be q into root n, which will be approximately 1 in 9, which will not pass the given constraints. So how to optimize this? Let's take some basic observations. For example, the given numbers are from 1 to 16 and we want to find the primes in this range. So because, for example, let's start traversing from 2 because 1 is not prime. Let's start from 2. So what numbers are affected by 2? We can say that 4 is not a prime because it has multiple of 2, as 4 is equal to 2 into 2. Similarly 6 because 2 into 3 is 6, and similarly 8 and so on. So because of these two, these all are considered as not prime because we got a we got a factor 2 of all these. So we can start traversing from 2. We can eliminate all the numbers which are divisible by it, and we can declare them as non-primes because we found at least one factor of it. So we can start traversing from 2 and we can remove all these, and similarly we can start from 3, and because of 3, what numbers are affected? Multiples of it. So 6, 9, 12, 15 and so on. And similarly we can start from 4, and because of 4, 8, 12, 16 and so on, and similarly all the numbers. So in this way we can traverse all the numbers and we can try to remove some numbers as prime because of other numbers as factors. So finally we can return which are prime or non-prime. If we observe this more carefully, starting from 2, we can declare all these as non-prime, firstly because of 2. And now coming to 3, according to this we have to start from 6 because it is the first multiple of 3 other than 3. So if we try to start from 6, it is already declared as non-prime. So is there a way to traverse it again? No, because we already declared it as non-prime. So there is no need to start from it again. So the first number that is affected by 3 is 9 because 6 is already considered by 2. Now coming to 4, it is already declared as non-prime according to 2. So any number which is a multiple of 4 is surely a multiple of any other number because 4 is non-prime. So there is no need to traverse 4 because all the numbers which are multiples of this are already considered non-prime because of the above numbers. Here too. Similarly coming to 5, the first multiple is 10, but 10 is already declared as non-prime according to 2. So no need to consider 10. Similarly 15 here and similarly 20 here. So the number that is originally affected by 5 is 25 and all the numbers after to it. So we can start from 25 and so on. And similarly 6, it is also not considered as prime by 2. So all the multiples of this are multiples of 2 as well, and those are already declared as non-prime. So there is no need to traverse all these again. And now coming to 7, the first factor is 14. It is already declared as non-prime, and similarly 21 in the third row, somewhere in the third row, and similarly all. And the first number affected by 7 is 49. So according to this, we can observe that for a number I, the actual contribution of it will start from I square, because all the numbers till that are already considered before, and the numbers which have to be declared non-prime according to the factor I is I square. So we can just traverse from 2 to max. We are traversing all, and if it is prime, only if it is prime. Initially all the numbers are declared as primes, and coming from 2, we will traverse its multiples only if it is non-prime, as discussed here according to 4 and 6. So if it is prime, we will enter the loop, and we can start from I square and go to mx, incrementing the I because we want multiples of I. So first it will be I square, the next time it will be I square plus I, and so on till less than or equal to mx. So we can declare is prime of j as 0 because we found it a factor which is I. So after completion of the loop, we can finally return is prime, where if the values if is prime is 1, it is a prime, else it is not a prime. So let's discuss the time complexity. For each prime number, the number of multiples we mark roughly is n by p, because we are entering this loop only if the number is prime. If the number is not prime, we will just increment the I and we go to the next number. And similarly, if we enter the loop, the maximum number of iterations are m by p, mx by p, because for a prime number p, we are incrementing p always. So first will be 2p, then 3p, and 4p, and so on m. So the maximum number will be m by p, because we are incrementing p every time. So it is n by p, approximate the number of multiples we mark. So the total number of operations are sigma n by p, where p is the first prime number 2 and till the last prime number less than max. So by some mathematical operations, we can achieve that the exact time complexity of this is n log n, the log n, and it is inside another log. So it is the time complexity of Sieve, and if we closely observe, it is greater than n because we have some other multiplicative factor with n. So it is greater than n, and if we assume that log n approximately tends to n, which is a very different assumption, but to get the maximum limit, we can assume this as n, because the n will be like this and log n will be very different. But if we assume that log n approximately n, we can get the upper bound which is surely less than n log n. So by Sieve we can find many numbers which are primes or not, and we can do queries efficiently as well. But according to Sieve, the time complexity now will be O of 1 per query, because we have already pre-computed the vector, and we can return 1 if each prime of j is 1, else 0. So the total time complexity will be O of q, because the time complexity of each query is 1. So now it will surely pass the given conditions. So coming to next one, let's discuss how to return the prime factors of a given number. For example, given number is 40. We have to return 2, 3 and 5, 1. So because 40 can be written as 2 power 3 into 5, we have to return the first prime factor 2 and the following power of it, and similarly the next number which is prime and a factor of it with the power, and so on. So again, coming to the basic idea, we can traverse all numbers from 2 till n, and we can maintain the number of times the present number is divisible. For example, we can just initially assume the count as 0, and if the number is prime, because we want only prime factors, and we computed the each prime using Sieve already before. So if the number is prime, we are finding whether it is divisible or not, and if it is divisible, we are counting the number of times it is divisible. For example, initially we are starting loop from 2. So coming to this, initially is 40 divisible by 2? Yes, because 40 by 2 is 20, and we are halving the number and incrementing the count, because 40 is 2 into 2 into 25. So the first 2 is because of 40, and the next one because of 20, and next one because of 10, and the next one because of 5. So we can divide the number until it is divisible by j, and we can increment count because we want in the terms of j power count. So after completion of this, if there is a count, because initially we have kept count is equal to 0. For example, if the number is 3 here and it is not divisible by 40 anymore initially, so finally the count is also 0. If the count is 0, it is not divisible, so we don't need to add. But if count is there, it means that it is divisible by it at least once. So we are pushing answer into we are pushing j comma count into answer. J is the prime factor and count is the power. So it is j power count. And the time complexity of this is n log n, because we can assume that we are traversing all the numbers from 2 to n. So it is approximately n. And for a given j, we are dividing the given number until it is divisible by that. So if we assume that the number is only 2 and we are counting the number until it is divisible by 2, it is approximately log n, because initially it will be n and the next time it will be n by 2 and so on. Why we assume 2 only here? Because for example, if given number is 10 and if we assume the time complexity with respect to 2, it will be highest because we are dividing by the smaller number, so it will result in a still larger number. So if we take assumption with respect to 5, after dividing it will become small, but if we divide 10 by 2, which is the least number, it will be 5 and we can just try to divide again. So we can assume the worst complexity using 2, because as we increase the number of iterations will be reduced and it is not a best estimation for worst time complexity. So we can assume it by 2 and the time complexity is n log n. Can we reduce it further? If we take a look and if we take an example, the given number is 35. Initially we are trying to traverse all the numbers from 2 to n. But can we reduce this loop? So the given number is 35 and the prime factors are 1, 5, 7 and 35. And the square root of 35 is approximately 5.9. So in the initial prime, we discussed that we can loop till root n and we can find whether there is any factor before root n, and if there exists here, it is not a prime, and if it does not exist, it is a prime. So now in the similar idea, let's discuss whether we can traverse till root n and will the exact code work. Will j is equal to 2 till j less than or equal to root n? Will the code work now? The answer is no. There should be a very small modification, because let's discuss here. Initially the root is 5.9, so we can traverse up to less than or equal to 6 or less than or equal to 5. Let's assume it as 6. So initially coming to the primes, 2 is not divisible, so it is not waste. Coming to 3, it is also not divisible, so ignore it. 4 is not a prime, we can ignore it as well. Now coming to 5, it is the first prime that is divisible by 35. So we found a number which is divisible, so we are making the count 0 and dividing it until it divides. So after dividing 35 by 5, the number is 7 and it is not divisible by 5 anymore. So the maximum power is 1 with respect to 5. So, and the next number is 6, which is not a prime, we can ignore it. So this loop is completed. We traversed all the numbers from 2 to 2 till root n. But now did we get all the prime factors? No. We missed 7 because it is greater than root n. So what if there are many other prime factors which are greater than root n and we missed? Here we can assume that there is only one prime factor which is 7, which is greater than root n. But what if we have many different prime factors which are not considered because the loop is still root n? The answer to this is, let's assume that there are two prime factors which are greater than root x, and let's assume those as x1 and x2. So both are greater than root x and they are x1 and x2. And if we multiply, it will be greater than x. Is this possible anymore? No, because the given number is x and the all prime factors should be multiplied and then the number we achieve is x. For example, if the given number is 40, we are multiplying 2 into 2 into 2 into 5 and then we are able to get 40. So is there a possibility of multiplying two prime factors and getting more than the given number? No. So we are sure that there cannot be greater than or equal to two prime factors which are greater than root n. So there can be at most one. And how can we find this further? So after completion of this root n, the number left is 7, because we did not traverse 7, we traversed only 6. So finally the number found is 7. So this is not equal to 1. It means that there is a prime factor which is greater than root n and it is prime. So finally we can push back into the answer num and 1, because the power is also 1 and the number is also the number left and which is surely a prime. So we can traverse till root n and similarly we can follow this. And finally, if the number is not 1, this means it is a prime factor which is greater than root n, and we can push back into the answer with the frequency 1. So in this way, by using Sieve, we can achieve query prime factors, and we can find prime factorization in root n log n, which is very optimal than n log n. So the code is very simple and we discussed before. So initially, the Sieve function returns the vector. We are traversing from 2 to max and finding whether the given number is prime, and marking all its multiples as non-prime, and finally returning the vector. And similarly, the prime factorization. Initially, we are taking the prime from Sieve and taking the answer and traversing from 2 till root n. And similarly, we are finding count, and if it is prime, we are dividing it until it divides the number. And finally, if count, it means that there is at least one power. So we are adding answer dot pushback j comma count. And similarly, after completion of the whole loop, we are checking whether the number is 1 or not. So if the number is 1, it means that all the prime factors are less than root n and are considered in the above loop. But what if the number is not 1? It means that it is a prime factor and it is greater than root n. So we are pushing back into the vector and finally getting the answer. So in this way we can find primes using Sieve in optimal time complexity. Drop a like and comment below. If you have any doubts, post the comments. See you in the next one.